Okay, thank you. So my name is Sylvain Dancette from, well, my home institution is indeed in Lyon, in Saint-Lyon. And then I am staying this year indeed as a research delegate at ELyTMaX. So this talk today will be about introduction, so quite basics of fracture mechanisms and fatigue behavior of metals. So just for you, for the audience, let's say, to be a little bit more familiar with where the defects you can find in parts or pieces, industrial components, where they may originate from, at least from the material point of view. So I will first give a few, let's say, introduction about materials microstructures and the way defects may arise from these microstructures and processes. Then I will talk a little bit about fracture mechanics, so how a material in the presence of defect is going to fail by one mechanism or the other. And then I will talk finally about fatigue behavior, so the behavior of mechanical behavior of materials under cyclic loading, so cyclic behavior, and the way crack indeed in this type of loading is likely to propagate in a material. So I guess this morning you had already an introduction about these types of of pictures, so catastrophic failures examples. So there are many of them in many applications, from aeronautic industry, from offshore industry, from everyday life. So usually what you see here and what is, let's say, the main point of this this series of lecture, risk management, it usually relates to that kind of unwanted fracture. So when we think about fracture, we usually think about something that we should have been able to avoid. So these examples here are some examples indeed of fracture scenarios that had a lot of implications, both in terms of human lives, both in terms of cost, etc. And we would like in the following to investigate a little bit where these kind of fracture can originate from the material point of view. But so this is only one side of fracture, because as you already probably know, fracture is also something that you come across every day in your life. In everyday life, you sometimes, without even knowing it, you use fracture as a way, for example, to open a can, for example, a Coca-Cola can, like in this example. When you open some food from food packaging, you also are doing fracture mechanics tests without even knowing it, actually. So there are many examples like this in everyday life where fracture is in fact something that is really controlled and something that has been very deeply engineered sometimes for many decades, just for people to be able to use it as a way, as a mechanism of achieving something in everyday life. So this pop can stay on tab here, for example, it took many years or many decades to engineer this design so that someone can easily open a can or a beverage like this. And this has to occur millions of times per week or even per day, without, most of the time, not without failure, because there is something in terms of failure of the material opening, but the mechanism itself works very in a very reliable way. So maybe one of the first message here that we would like to pass in this lecture is that fracture is not always something that you want to avoid. It's also sometimes something that you want to control, let's say, and manage. So coming back to the objectives of this lecture, let's say, what we would like to do here is to, well, try to understand a little bit of the link that exist between materials processes and the resulting microstructures in different classes of materials, and some of the defects that we can find in these microstructures, the defects that you will later have to be monitoring or to assess in terms of risk of failure. And then, based on this, we are going to look a little bit into the fundamentals of a fracture mechanics and mechanisms of fracture in the presence of defects. And then, as I said before, we are afterwards going to talk a little bit about the fatigue, cyclic behavior. So most of the illustrations that I will show in this presentation, they come from these books, and mostly the first one here. So if you want some details about many things that I will show today, you will find them in these very interesting Ashby, Ashby, Shackliffe, Sebon, Ashby, Jones, so very introductory and interesting books about material science and their links with processes and defects. Okay, so first I would like to remind you a little bit of the length scales and typical features that we can find in different families of materials. And maybe first what I have to do is to introduce or reintroduce these usual families of materials that we distinguish as engineers when we deal with materials. So basically you know the metals, steel, aluminum alloys, titanium alloys. We also tend to distinguish these metals from the ceramics materials, ceramics and glasses materials. And we will also distinguish metals on one end, ceramics and glasses on the other end, from the polymers and elastomeric materials. And as a matter of fact, all of these materials, classes of materials, families of materials, but when you look at them at a global, let's say, point of view, they usually offer similar mechanical properties, but not only mechanical properties, but mechanical, electrical, physical properties. So all of these families of materials, they also usually exhibit similar transformation processes. And we will see just after this that from the transformation processes, usually defects, potential defects will arise. And of course, the applications of these materials are also usually similar inside of a given family of material. Okay, so metals, ceramics and glasses, polymers and elastomers, and in between, you have a whole new class of new materials, these hybrids materials, composites, foams, where you can use the architecture of the material on top of the intrinsic properties of these materials to engineer new types of behavior, new types of physical properties. So coming back to the length scales, here with the example of metallic materials first, well, it is very important to bear in mind that the length scales in these materials, they go down to the nanometer or picometer even range when you talk about the atomic nuclei of the elements. You will come up to the, let's say, a few to the nanometer range when you talk about atoms themselves and atoms and the way they arrange in space, especially in crystalline arrangements. But as soon as you talk about atoms in these metals, you also start to talk about potential atomic scale defects like vacancies, missing atoms in the crystals, which may constitute, let's say, the smallest scale of defect you would find in materials. So from the atom packing, crystallographic packing, then you will come up to the upper length scale of grains. So in metals, most of the time, well, for almost all metals, the microstructure of a metal is made of grains inside of which you will find these atoms regularly arranged in a periodic way in these crystals. So the length scale of grains is usually in the order of magnitude of 1 or a few microns. And this starts to be also the order of magnitude in terms of length scale of potential cracks. The cracks you will maybe later want to monitor and to control a little bit during the lifetime of a part, of an engineering part. So on top of this scale, you will find now the scale of a surface roughness in a material, in a part. And this roughness is also most of the time in the order of a few microns. Sometimes a little bit below, sometimes a little bit above. And from the surface roughness, you can come up to the scale of potential cracks. So these cracks that may originate from several, let's say, mechanisms, but these cracks, these ones, you may be able to see them with naked eye, even sometimes, or with a very microscopic way of investigating a piece. So cracks, usually, you will see them in the length scale of about 1 millimeter. So the important thing here is that in metallic materials, so most of the properties, and these properties will control will control the way the material behaves in front of a crack. These properties, they come already down to the from the atomic scale. So the atoms and crystal packing, it will control, for example, the elastic properties of the material, the Young's modulus. Then at the upper scale, at the scale of the grains and inside of the grains, then the dislocations, the linear defect in the crystal will also control the strengths and also the toughness, we will see later, of the metallic material. And then obviously at the upper scale, at the scale of the cracks and surface roughness, this will have an impact on the fatigue behavior and also on friction and wear behavior of the materials. So you see that we have to keep in mind that there are many length scales at which these defects can be found, and many implications of the defects on engineering properties of the materials. So now there is we could perform the same type of analysis in ceramics and glasses. So again, in most of the ceramic materials, we can find this crystalline structure. So again, with the same typical length scale of a few microns, and together with this scale of the grains, inside of which we can find the molecules and atoms constituting the ceramic materials. Inside of the grains, again, you will find the length scale of the first cracks and first defects that will later on control the way the ceramics are going to behave under stress. And compared to the crystalline ceramics, well, the structure of glasses is amorphous by definition. So you don't have grains in glasses, but this random packing of atoms, but still you will have such micro cracks here at the scale of a few microns, and these will also control some of the fracture mechanism of the glasses when loaded in a mechanical way, say. And of course, at the top scale, you will indeed also find the cracks and surface defects, just as you would find them in metals. But maybe the very important thing here with ceramics and glasses is that, well, these materials, they have very stiff atomic bonds and a high lattice friction inside of the grains in the case of crystalline materials, crystalline ceramics materials, which means that they usually show very high Young's modulus and very high hardness and very low toughness. So these materials are usually very brittle, which means that in these materials, even very, very small cracks, very small defects at the length scale of a few microns, they may already be very detrimental for the fracture behavior. Okay, so now we can say a little bit about the polymers and elastomers. So the huge difference of polymers and elastomers with respect to ceramics and metals here is obviously that the microstructure in itself is not really controlled by atomic arrangement anymore, but these times it is rather controlled by the ways the macromolecules, these long, very long molecules constituting the chains, the molecular chains in the polymer, the way they are arranged, let's say, in the material, with sometimes an amorphous structure, sometimes semi-crystalline structure. And all of this, again, will take place at length scales in the order of a few microns. And when you load these macromolecular materials, again, under the effect of loading, under the effect of temperature, you will sometimes start to initiate this type of defects, these crazes, so the way macromolecules starts to locally range under the effect of loading. And these crazes or macrocracks, they already constitute some kind of defects that will later on impact the way the polymer behaves under loading and the way it will fail in the end. So in these polymers, the arrangement of the macromolecules has a strong impact on mechanical properties and therefore on fracture. But we can also add that, well, most of these materials are also used in the shape of the let's say arrangement in applications such as foams or composite materials. And in that case, there is another length scale that comes at play, which is in fact on top of the architecture of the macromolecules, the architecture of the foam itself, or of the composite itself, the fibers, for example, in the matrix, that will also have a strong impact on the mechanical behavior and fracture behavior of the materials. Okay, so that was a short introduction about materials families. And then I would like to give you a short, a few examples, let's say, of processes, materials, and processing, and the way they may impact the type of defects we can find in these materials and microstructures. So one of the example, very common example, is metal casting. Metal casting, you can find it in tons of applications, for example, in the automotive industry, but also in the aeronautic industry. So metal casting basically consists of pouring some liquid metal into some mold, for example, a sand mold like this one. And well, this liquid metal will simply cool down to room temperature, and during cooling, it will solidify and will end up with a rather potentially complex shape, the shape which is the near net shape of the component you want to use in the end. So the problem with this, obviously, is that you have a liquid that will have to undergo solidification. And when you start to think about solidification, it implies, in fact, a lot of metallurgical transformations and metallurgical phenomena, starting, as illustrated here, started from the way, in fact, the germs, the very germs of solid are going to initiate from the liquid. And you can see here in this illustration that the way the grain are going to grow from the liquid, it will be different if this happens on the mold wall, for example. So on the wall, on the very exterior of the mold, with a direct contact with the sand mold in this case. In which case you will most likely have such columnar grains here that will occur during solidification. And compared to this, if solidification occurs in the liquid, in the bulk, let's say, of the liquid, then you will have another type of initiation for nucleation and growth of the crystals within the melt. And then you will end up with a different microstructure, so most likely equiaxed grains. So again, you see here the scales in such solidification structure. The scale of the grains is usually in the order of millimeters compared to the usual scale of the grains in fine grained materials, engineering materials, which was, as we introduced before, rather in the order of a few tenths of microns, for example. But the important thing here is this. In fact, depending on how the liquid will solidify into some solid material, then there may be a whole range of defects that can occur during the solidification process. And one example is this kind of micro shrinkage that can occur during the solidification. You can see that these micro shrinkage defects, they can be as huge as several hundreds of micrometers. And these micro shrinkage, they directly originate from the fact that there is some change in the capacity of the materials between the liquid state and the solid state. And since the whole thing has to cool down under constrained, let's say, geometry and constrained cooling rates, it is not unusual to find such kind of micro shrinkage defect in a mold, in a metal cast. Sorry. So this is the example of an aluminum alloy, a cast aluminum alloy, but you may find similar defects in a whole range of cast irons, for example. Okay, so casting defects can range from these kinds of shrinkages, micro shrinkages, but it can also be just gas pores, gas that was trapped in the liquid and trapped during solidifications. But you can also find during this solidification process a lot of oxides and impurities that tend to migrate on the grain boundaries during the solidification, depending on the chemical composition of the metal. So all of these are potential defects that will most likely have a rather strong impact on the fatigue properties of the material. So another usual type of deformation processing of metals and alloys. This is here the example of a rolling. So usually the metals, once they have been cast into slabs, for example, at some point, if you want to produce sheets or you want to produce parts that will be later formed, well, you have to roll them. So you have to produce them in the shape of sheets, for example. And this implies some hot deformation processing, like this rolling process. And again, if you subject a metal to that kind of rolling process, then you see that there will be some strong evolution of the microstructure inside of the material from the initially equiaxed grain, potentially that we can find in the core of a cast slab, for example. And these grains here will be severely deformed and severely reoriented, let's say, in the course of the process, implying potentially several phase transformation or microstructural transformation mechanisms like recovery, recrystallization of the material, but also in steels, for example, there will be definitely some phase transformation, some change of crystal structure from high temperature to low temperature. And all of this, again, will have a strong impact on the resulting microstructure. And along the way, you may find different types of defects due to the rolling process, starting, for example, with alignments of second phases in the microstructure, as you can see here. So in that case, this is a dual phase steel, an automotive steel. And in this particular case, what you can see in black here, compared to the background, is the so-called martensite phase of steel, which is very hard and very brittle, providing a lot of strength to the material. But you can also start to note that when these martensite islands tend to be a little bit too much segregated or a little bit too much aligned in the same directions, then this will start to potentially cause some troubles in terms of the isotropy of the mechanical behavior. So already here we can see that the rolling process in that particular case induced some severe orientation, let's say, of the phases in the materials, and again, this will have some impact on fracture properties. Okay. Another usual example in metallic alloys is the case of heat treatment. So most metallic alloys after deformation processing, which was itself after solidification, for example, after casting and deformation processing, most of the time these metallic alloys, they are heat treated. So particular heat treatments, and especially in order to optimize the strength of the material. This can be the example of an aluminum alloy, for example, here. So the aluminum alloy that was casted beforehand, at some point, in the parts that will have an engineering interest, let's say, this part has to be heat treated by that kind of solution heat treatment followed by precipitation heat treatment. And the goal of this precipitation heat treatment here is to induce some second phases in the material, which will provide some strengths, optimized strengths of the material. And again, depending on the type of precipitation heat treatment, depending on how well you control or not the temperature or the time during this precipitation heat treatment, you may have several types of second phases, particles here, precipitates, from coherent nanometric precipitates to coarser semi-coherent or incoherent precipitates. And again, depending on the nature of these precipitates occurring inside of the grains here during the treatment, this may have a very strong consequence, a very strong impact on both mechanical properties of the material, strength, yield strength, for example, but also on fracture properties. And it is not uncommon that such second phase particle here constitutes, as we will see later, the crack initiation sites in the microstructure of the material, in that case, of the metallic alloy. Okay. So another example here that may apply to ceramics, for example, powder processing. So powder processing is a very common process, both for high performance ceramics and also for many metals, and especially today with the advent of additive manufacturing techniques, such as laser powder bed fusion, for example. All of these processes are based on the first place on powder. So anyway, when you start from powder in a material, this powder at some point has to be, let's say, a little bit compacted to, let's say, the shape of the final piece that you want to produce. And if you do that with the help both of pressure and temperature, then there is this compaction process that will occur, tending to reduce, let's say, the space and these cavities here between the original particles of the powder. So with this compaction process, you start from powder with a very lot of free space, free volume between the particles, and thanks to the compaction and thanks to temperature in a furnace, then diffusion will allow to achieve a material that is close to compact. But again, this material is in fact only close to compact. It is not 100% compact. So the residual pores, residual voids here that you may find at the triple points, for example, in this microstructure, you have some example here on the right in this picture, which is a titanium alloy that was produced by such a kind of powder processing. These residual pores, as large as sometimes as a few dozens of micrometers, well, they are here in the microstructure, and they constitute potential initiation sites and potential sites for early fracture, let's say, in the material during service. So we have to keep in mind that when we talk about ceramics, and especially high performance ceramics, most of the time they are obtained from that kind of sintering processes, of powder processing. And there is always some residual porosity in these materials, which will have a strong impact later on during service on the fracture behavior of the material. And since ceramic materials in general are very brittle, again, very small defects such as these pores here may have a strong impact on the mechanical behavior and fracture behavior. So size of the pores here is very critical in these materials. So another type of process, common process in metallic materials is welding. So It is very usual for metallic parts, once they have been produced, well, it is very usual that they have to be welded at some point in order to weld it together. So it can be several sheets welded, it can be several more bigger pieces welded together, because it is usually impossible to produce meter size, let's say, parts, industrial part, without having to produce it beforehand from several smaller parts in terms of sheets or in terms of any shapes that. So anyway, at some point in an industrial part, it is very, very common to find welds in the materials. And again, during the welding process, there will be some strong evolution of the microstructure, and especially evolution of the local microstructure. So the local microstructure of the weld compared to the microstructure of the base metals on these parts. And this, well, due to the thermal cycles that is experienced locally in the weld, and depending on the type of a metallic alloy, aluminum alloy, for example, or steel alloy, then you will have different types of evolution of the mechanical properties, local mechanical properties. So this is the example of a alloy steel, where you will experience some strong hardening in the so-called heat affected zone here in the vicinity of the weld. But in these steels, depending on the way the weld was produced, you may also have a fusion zone that has a behavior that is rather similar to the behavior of the base metal. But sometimes you may also have some softening of the fusion zone compared to the base metal. And this is usually also the case in aluminum alloys. So aluminum alloys, which, as we said before, are usually optimized for strength, thanks to precipitation heat treatments. When you weld these aluminum alloys, usually the base metal has a hardness and a strength that is much higher than the potential hardness and strength of the material inside of the weld. So this is, again, potentially a problem. But besides this, with the welding process, you will very commonly see several types of defects inside of the welds. And we have here the example of a resistance spot weld in automotive steels. So resistance spot welding being used widely used as a common welding processes in the automotive industry when you want to join automotive sheets. So in such high strength steel resistance spot weld, it is not unusual to see several types of defects, such as liquid metal embrittlement cracks, for example, or such as internal pores, which again may be harmful to the mechanical properties. So this harmfulness has to be checked when you have to deal with a part, with a material that, or part of a material that has been welded at some point. Okay, last example, if I remember well, yes, last example in the case of polymer materials, thermoplastic polymer materials. So in the case of polymers, again, we introduce the fact that most of the mechanical behavior is due to the arrangement of the macromolecules, molecular chains in the polymers. And this is, of course, strongly dependent on the glass transition temperature. So if you deform the material close to the glass transition temperature, then the molecular chains will have a lot of ease to reorient and to reorganize them upon loading. While if you do that at a lower temperature compared to the glass transition temperature, then they will most likely have more difficulty to reorganize. And in that case, it is not uncommon to see that kind of defects, these crazes that can be found in such materials. It can be crazes when you load in tension. It can be also shear bands when you load rather in compression. So anyway, when you load these polymer materials, well, there will be, due to the ease or unease of rearrangement of the molecules, there will be some kind of defects occurring, or micro defects occurring in the microstructure. And well, when we talk, for example, here about molding, polymer molding, you see here that the initial form of the polymer material, when you heat it at a sufficient temperature above the glass transition temperature, and when you inject hot gas under pressure in the material, so this can allow to achieve the final shape of a bottle, for example, in that particular example. And during this molding process, again, as illustrated on the left, there will be significant rearrangement of the molecules that will first align, let's say, in that example, during the molding process. And afterwards, during cooling, there will be some reorganization of the molecules in terms, for example, of a partial crystallization, of the molecules, and potential, again, apparition of such microcrazes after cooling when the part starts to be deformed. So with these examples, so I wanted to illustrate well, a few of these typical defects that we can find in engineering materials from the different families of materials. So at this point, the question now is, how does the material, once we have it in the end, how does it behave in the presence of such a defect? So most of the time, you have just seen that the materials will present some defects, sometimes micro scale defects, sometimes millimeter scale defects in the parts. And we want to understand now a little bit of how this will impact the fracture and the fracture mechanisms of the material. So here again, so we have to recall some of these fundamental mechanical properties of the materials, and we have to distinguish what we call strengths and what we call fracture toughness or toughness too. So this illustration here shows that when you have a sample, so sample of material, so it can be a tensile sample in that case, if the material has a defect inside it, so a crack, for example, crack, any crack that could be obtained from the different processes we saw beforehand. Well, depending on the relative, let's say, value of these different properties, strength and toughness, you may see the material either deform like this, so plastically deform, which in that case will tend to blunt a little bit the crack before fracture, and this is the case of a tough material, a material with a ductile behavior. And on the other hand, when you have rather brittle materials with the same type of loading and the same initial crack, so this crack inside of the sample will rather tend to initiate sudden fracture or fast fracture of the material. So the key properties, again, controlling the transition from that behavior, brittle behavior, to the tough behavior, ductile behavior, the key properties here are the strengths, relative strengths, and toughness levels. So strengths, we can define it as the resistance to plastic flow, and it is usually measured with a property like the yield stress in the material. And the toughness here, compared to strengths, we can describe it as the resistance to crack propagation. So a material that is tough, like this one, it is easily able to resist crack propagation. And in that case, the crack will rather blunt than propagate. And in the case of a low toughness material, so the crack in that case will rather propagate and in an unstable way. So strength, toughness allow us to distinguish these two extreme cases of a fracture behavior, the ductile behavior, usually occurring with materials with low strength but high toughness, and the brittle behavior, that one, usually occurring in materials such as ceramics with a very high strength but very low toughness. Okay, So when you want to quickly assess these types of mechanical behaviors, it is not uncommon in the industry to perform some of these macroscopic tests. So this crack extension test, for example, here in that case, you cut a small pre-crack in the sample and you load it in tension and just register how the load is evolving with the extension. And doing this, you can measure the energy that is dissipated during fracture. This is one easy way of proceeding. The other usual and easy way of measuring some estimate of material toughness is to perform this kind of impact test. So you have a sample with a pre-notch. You put it, for example, in a device that will be allowed to hit it with a mass, and measuring knowing the initial potential energy of the mass. When you know the height of the mass beforehand, before fracture, you can easily afterwards measure how much energy was dissipated in fracture if you just measure how the height of the mass after fracture. Okay, so this is the usual impact test. That version would be the ISO test, and you can also easily find it with the Sharpie impact test, which would be rather a case of three-point bending. So the problem with these tests here is that they are maybe easy to perform, relatively easy. So it is relatively easy to measure some kind of fracture energy out of this, but this is not really a true material property, because all of these ways of measuring fracture here depend on the sample sizes, sample dimensions, shape of the crack, etc. So these are not intrinsic material properties. So it is useful these tests for quality ranking, quality control, but not for measuring intrinsic material properties. But still, if you perform that kind of impact test, Sharpie impact test, for example, you can easily see in that picture here, so this is in French, I'm sorry. So this is steel, mild steel, this is aluminum. We can easily see here that performing this kind of impact test, you can clearly see how steel, for example, will tend to present a decreasing fracture energy when you lower the service temperature, so the temperature of the mechanical test. And most of the steels, especially maybe 100 years ago or 150 years ago, most of the steels, they were not really, let's say, precisely controlled in terms of chemical composition and so on. And well, 100 years ago, it was not uncommon to have that kind of ductile to brittle transition at temperatures such as close to the room temperature, in fact. So obviously, when you have a material like a structural material like steel that shows that kind of a ductile here with a lot of energy to brittle with a very low fracture energy transition, and this can be a problem. Okay, and with this impact test, it is quite easy, at least qualitatively, to assess the transition temperature of the behavior. You can also see here that in the case of aluminum alloys, for example, this transition from ductile to brittle or brittle to ductile is not occurring. And this is related in that particular case to the crystallographic structure of the material and to the fact that aluminum alloys are face-centered cubic crystals, mostly. So, well, again, these macroscopic measures of fracture, they greatly depend on the test conditions and on the shapes and of the samples. So they can be used for ranking of materials, but not for measuring intrinsic mechanical properties of one class of material. So if we want to measure something that is more intrinsic to the material, then we have to start looking at what is happening at the crack. And well, basically, when you have a sample that presents a crack, when you load it here in tension, for example, you see here that the stresses are redistributing in the vicinity of the crack. So there is some kind of stress concentration at the crack tip that is illustrated here. So very close to the crack tip, you have very high stresses, and as you go away from the crack tip, the stress is decreasing and decreasing, in fact, to the remote stress level, the macroscopic stress level that is applied to that tensile sample. So what we can see here is that, well, there are several analytical estimates of the local crack, local stress concentration in the vicinity of this crack here. And we can see here that, well, in the very vicinity of the crack tip, in the very vicinity of the crack tip, the local stress here, diverging local stress, is in fact proportional to this factor that we call the stress intensity factor, which depends on the remote stress and on the square root of the length of the crack, the little c here. So this is the stress intensity factor. And again, anywhere at any position away from the crack, so at any position R, the local stress is in fact proportional to this stress intensity factor. So this will help us because these stress intensity factors, they are usually very well known in many engineering situations. So you have several examples here of samples with either continued screw cracks, with a single edge notch here, with a crack submitted to internal pressure. In all of these common engineering cases, or three-point bending in that case, it is easy to estimate this so-called stress intensity factor K, which depends always on the remote stress and on the square root of the crack length, little c. So knowing this, we can in fact come up with some ways of measuring what we call fracture toughness. And to do that, we will simply perform one of these tests, so the tensile test with a given continued through crack in the material, for example, or that compact tension tests loading the sample with an edge crack, such as the one that was represented here. And because we know the way the stress intensity factor is evolving during these tests, and evolving especially during the tests in terms of stress applied to the sample and in terms of displacement, it is easy to come up, relatively easy to come up with the critical stress, the stress leading to fracture in that test, and relate that critical stress to some critical level of the stress intensity factor. Okay? So since we know the stress intensity factor, when we measure it at the fracture stress, that sigma dot here, then we can come up with what we call the critical stress intensity factor, which is also called simply fracture toughness. So K1C is the so-called plane strain fracture toughness of the material. And this type, this K1C, depending on the singularity of the stresses in the material, it is really a material property that is independent of the type of the geometry, for example, of the sample, of the material and of the sample. So K1C here, critical value of the stress intensity factor, compared to all of these previous macroscopic estimates of fracture energy. So these were not intrinsic material properties, but this time K1C, the fracture toughness, is an intrinsic material property. Material that can be measured on one test and used on another test or other part in order to assess when fracture will likely occur. Okay. So there is this dual side of the fracture mechanism here that we can now look from the energetic point of view. So anytime when you create a crack, in fact, you add additional surfaces in the material. So when the crack propagates, or when you cut the cube here, you obviously create two new surfaces. And this is a necessary condition for a crack to propagate in the material. And this means that the energy required to propagate a crack has to be at least corresponding, but usually much more than this, at least the value of the new surfaces, new surface energy that was creating during the fracture process. Okay, so we have this surface energy, two new surfaces, then we have a fracture energy that has to be minimum 2 times two surfaces, this fracture surface energy times the increment of area during crack propagation. So most of the time, the actual fracture energy that is dissipated during fracture, it is in fact much more than this, much more than 2 times the surface energy. And this is especially related to the plasticity mechanisms and to the deformation mechanisms occurring during the fracture process, as we will see later. But anyway, another way of measuring, in that case, the fracture properties of a material is what we call here the mode 1 toughness. So toughness compared, so this is a little bit tricky because the previous one was called fracture toughness. Fracture toughness relates to this K1C value. And when we talk in terms of fracture, but this dealing with the fracture energy, we call it toughness. Toughness without the fracture toughness. Toughness, or the critical energy release rate that has to be dissipated in terms of energy per unit surface in the crack propagation. And as a matter of fact, these two measures of fracture, so the fracture toughness, K1C, and the toughness G1C, they are related together and related especially via the Young's modulus of the material. Okay. So now we have an overview of these values of fracture toughness here. The vertical axis is a fracture toughness as a function of the Young's modulus of several materials, several of the different classes of materials. So we have the metals here on top, we have the elastomers and the foams here in the bottom. And you can see here that this fracture toughness K1C can range from over several decades in terms of order of magnitude, from lower than 1 megapascal squared meter to, in the case of metals, more than 100 megapascals squared meter. And if we relate these two values, so fracture toughness and Young's modulus, again, when you look at such maps, these so-called HB maps, then you can come up again with the estimate of the toughness itself, toughness in terms of energy per squared per area dissipated in fracture. So if we talk in terms of energy per unit surface, some of the metals have fracture energy as high as 100 kilojoules per square meter, while some of the most brittle materials, such as ceramics, they have fracture energy as low as 0.01 kilojoules per square meter, so a few tens of joules per square meter. Okay, so with this, we are reaching a point where we want to describe what is the critical crack size that is indeed likely to yield fracture. So again, we just described beforehand that the critical fracture toughness is related to the failure stress of the sample and at failure stress at a given crack size. So if we try to estimate the failure stress of a material at a given crack size when the stress is in fact reaching the value of the yield strength, then if you come up with that equation where the failure stress has to be higher than the yield strength, then at the transition between these two, you can define the critical crack size. So this critical crack size, say crit here. And if you define the critical crack size, determining sigma f equal sigma y here, then you will come up with that expression of the critical crack size, which will depend on the fracture toughness K1C squared over the yield strength squared. Okay? So this means that in these materials, most of the in these engineering materials, the critical crack size that can be found in a piece is in fact heavily depending both on the fracture toughness, but not only on fracture toughness, it is also depending on the yield strength. Because obviously, if the yield strength of the material is very low, then the material itself will start to deform before cracking. So material deforming before cracking will not fail in a brittle way. But on the opposite, a material with a very low fracture toughness and very high strength, this will not have the opportunity to yield before fracture, and it will fail in a sudden and brittle way. So this is a usual relation that allows us to determine the order of magnitudes of a critical crack size in the families of materials, which is again severely depending on both fracture toughness and the yield strength. And as a matter of fact, damage tolerance in these materials, in metals, damage tolerance is very high. It is high because most of metals have a very high toughness, K1C, and sometimes small, sometimes a little bit large yield strengths, but because of this high toughness, the metals, they can accept cracks as big as a few millimeters, for example, in a structure, without these cracks being very detrimental for the in-service property. And as compared to this, in ceramics this time have a very low fracture toughness. And well, in these materials with a very low fracture toughness, if the fracture toughness is very low, then the critical crack size is also very, very low. So in ceramics in general, even a very, very small defect, like a few microns porosity or a few micro crack in the grains, even such very small defect can yield to brittle and fast fracture. And again, if you use these charts here, HB charts here of fracture toughness as a function of yield strength, then you come up again with an easy way to assess the orders of magnitudes of the critical crack size in the materials. And again, with materials such as metals with a very high fracture toughness and moderate yield strength, then the critical crack size might be as high as a few tens or a few hundreds or even a few thousands of millimeters. Okay, so it is not unusual to find defects in the order of magnitude of millimeters in metals. In most pieces, these defects are not detrimental in service properties, at least static service properties. But if you look at ceramics, most ceramics, and if you look at the values of fracture toughness and yield strength in these materials, so in ceramics, defects as small as a few, again, tens of microns, they will be most likely very, very detrimental for fracture. Okay. So in ceramics, I have to hurry up a little bit, I see, because time is running. In ceramics, there is another interesting property, an interesting fact that the strength of a brittle material, such as ceramics, it is heavily depending on the way it is loaded. So in ceramics, if you load it in tension, which is illustrated here, so the behavior in tension will be most likely dictated by the largest and the baddest, let's say, the longest crack in the material. So if you load the brittle material in tension, you may have a lot of crack inside it. Only the biggest one, and the one that is mostly perpendicular oriented with respect to the stress, this will be the critical one, so the critical defect that will drive a fracture. And as opposed to that, the same material, if you load it this time in compression instead of tension, well, you will not tend to open the crack, but because of the shear or of the compression, loading type, then all of these small cracks, small defects present in the material, they will start to propagate in a stable way, let's say. And the result of this, and deviation and stable propagation of the crack in compression, the result is that, well, the fracture stress, usually in brittle materials, might be as high as 50 times bigger in compression compared to tension. So same material, but if you load it in tension, it will have a given fracture stress. If you load it in compression, this fracture stress might be as high as 15 times the fracture stress in tension, just because of the way these defects here inside of the material will be, in fact, either stably propagating or critically propagating in an unstable way in the case of tension. Okay. So maybe I will not go too much into the details of statistical variation. So in these, maybe just in one word, in these brittle materials, you cannot define a unique value of strength when you load it in strip-on bending, for example, or if you load a brittle material like a ceramic in tension, you will not be able to measure a given value of fracture stress if you load 10 or 100 samples, for example, but you will rather obtain a distribution of the fracture stress. And this is just to mention that there is a usual law that is used for describing the survival probability of such brittle samples, which is called Weibull law, which is that kind of exponential law, allowing to define a stress, sigma 0, and a Weibull modulus with the value of the modulus driving how high the deviation and the scattering of strengths might be among materials. So I have to, well, I would like to just introduce a little bit more into the details of the different fracture processes occurring at the microstructure scale, let's say, in the materials, starting with the way brittle material tend to fail. And in brittle materials like quenched steel, for example, or most ceramics, you will most likely see that kind of a brittle cleavage fracture. So in that kind of cleavage fracture, what you see, in fact, is something that is due to the stress concentration at the crack tip. So if you have a defect in the ceramic material, like these micro cracks, as we introduced before, at the crack tip, there is underloading some stress concentration. And in these brittle and hard materials, since they are very hard, they do not have the ability to accommodate plastic deformation ahead of the crack tip, so that the stress can reach very high levels, very close to the level that is necessary to break the atomic bonds between the atoms. So this is what we call what we call cleavage, and obviously, in such materials, fracture occurs in a very sudden and fast way, with a very sudden crack propagation as soon as the stresses at the crack tip exceeds that critical level that is in fact very close to the ideal strength of the material. But it is interesting to note that most FCC materials, for example, face-centered cubic materials such as aluminum alloys, they will never exhibit such kind of cleavage fracture because they have a crystalline structure that is easily deformed by many slip systems. So cleavage fracture is an example of very brittle fracture. Another one is the so-called brittle intergranular fracture. I guess my colleague Nicolas will talk a little bit more about it later. So in the case of intergranular fracture, well, because of the grain structure of the materials, of most ceramics and metals, if you happen to have some grain boundary segregations, impurities, for example, in the alloy that tend to develop at the grain boundaries, and if these impurities are brittle, which is not uncommon, then you have, let's say, an easy path for crack along the grain boundaries. And this, of course, might be accelerated by the environment, for example, if you have a corrosive environment in the material. And, well, in the case of intergranular fracture, then, well, the easy path for the crack is at the grain boundaries because of these segregation or impurities that may be present in the case of alloys. So intergranular cracking is another example of brittle material fracture. So now we come up to the ductile behavior. So ductile behavior of most metals, for example. And in this case, in the case of ductile behavior, you see that many engineering materials we saw before, they present some kind of second phase particles or inclusions inside of the microstructure. So in such case, when there are such kinds of second phase particles, and when we deform the material in tension, so the material itself is rather ductile, so most metals again are ductile with a strong ability to deform plastically before fracture. And what is happening in that case is that, well, the voids, cavities tend to initiate from these second phase particles or inclusions that are present from the chemical composition of the steel. So these inclusions here act as stress concentration sites. Then at some point they allow to initiate some cavities, some voids in the bulk of the material. And when you continue loading the material, then you will have the void that will grow. At some points, they will grow so much that they will start to coalesce, to bridge together. So this is what we call the cross. And the final stage where the void coalesce together is called coalescence. And this is what is leading in the end to the final fracture of the material. So when you look at such metal here, for example, at the mild steel fracture surface, if you look at it in a scanning electron microscope, for example, it is very probable that you will see that kind of dimples at the fracture surface. And so the dimples here are these circular pattern here, corresponding in fact to the voids that you look at that you look at from the top. If you look from the top here on the fracture surface, you see the result of these void growths that coalesce together, and it is also noticeable to see that you can also retrieve some of these inclusions. Here, you have the original inclusions here that was at the source of a nucleation of these final crack, ductile crack. Okay, so ductile fracture, and well, this is in the case of ductile material also what is happening when you have a crack. When you have an initial crack in the parts. So in that case, when you have a crack, again, because of stress concentration ahead of the crack, the ductile material will tend to develop that kind of plastic zone ahead of the crack tip. And inside of this plastic zone, locally, because of the crack, then you will have this mechanism of initiation or coalescence of a fracture occurring at the crack tip. And because of this whole mechanism of ductile fracture occurring at the crack tip, there is a lot of energy, a lot of plastic part that is dissipated during the fracture process. And for this reason, the work of fracture, the fracture toughness itself in such ductile materials, in the presence of a crack, it is very, very high and much, much higher, thousands or hundreds or thousand times higher than in the case of cleavage, for example. Okay, so last example of a fracture mechanism and especially in the case of hybrids or composite materials. Well, this example illustrates how a crack may propagate in a composite material. So when you have a material made of a matrix, which can be a polymer matrix, for example, and of fibers, strong and hard fibers, like these glass fibers, for example, then if you look at the fracture properties of each of these phases separately, then you can see that the polymer matrix itself is not a very tough material. So 3 megapascal squared meter is rather low for fracture toughness compared to metals, for example. The glass fiber itself, it is very strong and very stiff, but also very, very, very brittle. So even less than the polymer matrix. So less than 1 megapascal squared meter. When you can see here that when you elaborate a composite material with the matrix plus the fibers, due to the arrangement of the fibers and its interplay, let's say, with the matrix, the fracture toughness of the composite material can range up to 10 megapascal squared meters. So because not only of the individual phases, but on the way they are interconnected together, and they are, in fact, they adhere to each other. When a crack tends to propagate in such kind of composite materials, the crack tends to be deviated and to initiate additional fracture mechanisms, for example, in the case of a fiber fracture here. And then afterwards, there will also be some energy dissipated in the debonding and in the pull-out of the fiber itself. And all of these dissipation mechanisms tend to produce a fracture toughness that is, in the end, much higher in the composite material compared to the individual material matrices. Okay, so in these materials, so architecturing, let's say, the way the phases are organized together, it can be a very effective way to manipulate and to increase, especially, the toughness of the material, and especially in that case to retard, to delay the crack propagation and the consequence of crack propagation in a industrial component, for example. So I see that time is running. Only 20 minutes left, right? 15, yeah. Yeah. So I will say a few words about cyclic loading. So cyclic loading, I guess you're kind of familiar with this. Cyclic loading relates to is related to the fact that a component during loading, during service loading, will most likely not undergo only a monotonic stressing, a monotonic loading, but most likely, most of the engineering components, they will undergo that kind of cyclic with various amplitudes of loading during lifetime. And the fact is that there are tons of examples of cyclic loading in everyday life. But the fact is that in a material, what we just described was that fracture occurs at a critical stress for a critical crack size when you load the material monotonously. But when we talk here and now about cyclic loading, the fact is that even a ductile material, like a metal, can fail by fatigue or cyclic loading, even if the stress is much lower, for example, than the yield strength. And this is the problem of fatigue loading. So usually, when we talk about fatigue, we distinguish acoustic vibrations, in which case the stress amplitude will be very small compared to the yield strength of the alloy. We can talk about high cycle fatigue, in which case the strength will be still smaller than the yield strength, and in that case, the material is expected to undergo a very large number of cyclic cycles before fracture. So this is why it is called high cycle fatigue. And on the other side, well, if you load the material with a very high stress level especially high compared to the yield strength level, then we come down to what is called low cycle fatigue, in which case, indeed, if you load the material to stress level that is close to the fracture stress in tension, for example, obviously, you will not perform a lot of cycles before fracture. So if you load it directly to the tensile strength, you will only perform one cycle of loading before fracture, right? So acoustic vibration, high cycle fatigue, low cycle fatigue, all of these, usually it is common to find information about the material behavior in terms of fatigue endurance with this so-called Wöhler curve. So Wöhler curve or endurance limit is a graph in which you plot the amplitude of stress. So if you load the material using cyclic loading, then you can define the amplitude of the stress, sigma max minus sigma min. You can define the mean stress, sigma max plus sigma min over 2. And you can also define the loading ratio, sigma min over sigma max. So when you talk about Wöhler curve or endurance limit, this usually refers to zero mean stress. So cyclic loading centered about zero stress, 0 megapascal. And in this kind of graph, you will typically describe how much cycles to fracture are required at a given stress amplitude. So if you load the material at the tensile strength, obviously, already at one cycle, the material fails. But if you load the material at a stress level that is very low, and especially very low compared to the yield strength, then it is not unusual to reach as much as 10 to the power 7, 10 to the power 8, 10 to the power 9 cycles before fracture. And usually, that Wöhler curve tends to exhibit some kind of a saturating behavior on the right here. And that allows usually to define what is called the endurance limit, which is by definition defined as the stress amplitude allowing the material to reach 10 to the power 7 cycles before fracture. Okay? So this endurance limit here, sigma E, is a usual property that can be found in most of the database along with the yield strength or the tensile strength of a material. So maybe I will drop this in the interest of time. So usually real life fatigue is not at constant stress and not especially at a zero mean stress, but it can usually occur at a positive or negative mean stress. It can also occur with various amplitudes of stresses along the lifetime, and many examples and many analytical relations allow to assess what would be the endurance, let's say, of a part when the material is not loaded at constant stress amplitude and at a zero mean stress. So anyway, I will not go too much into the details here. But that I want to spend a little bit of the time remaining to talk about how the crack, in fact, initiates and propagates in a material when you load it under cyclic loading. So most of the time when we talk about metals during fatting loading, then it is usual to distinguish these three stages of fatigue cracking. So the first stage would be the crack initiation stage. And usually in a material that didn't have really big defects at the surface, even with a polished fracture surface, let's say, the initiation stage will occur when local slip bands will start to develop at a micro, let's say, at the scale of the surface roughness, let's say, because of the roughness of the material, there will be a local variation of the local stress, which will yield to some local gliding of dislocation in the vicinity of a small pre-defect. And this is what is usually called persistent gliding bands. So in this way, because of local gliding, even with a material that was close to smooth in the beginning, plasticity around this surface roughness will start to develop what we call these persistent gliding bands. And these persistent gliding bands, they may occur on several locations on the material, but at some point, one of these persistent gliding bands may take advantage over the others, and this most critical one will later on propagate. And this defines what we call later on stage 2, the crack growing, propagation of the crack during cyclic loading. And once a big crack is starting to propagate, usually you see that in the beginning, initiation cracks were not especially aligned with the stress, and they are most likely related to the plasticity and occurring more or less at 45 degrees with respect to the tensile load here. But when the loading stress increases, when the loading cycles increases, you can see that the crack that initiated at 45 degrees, or more or less, they tend to propagate more and more perpendicular to the macroscopic stress. So this is a usual mode 1 opening crack behavior. So at the end, when this crack will have reached the critical size, then we will reach the final stage of fatigue, which is called the fast fracture. So one interesting fact here is that when we look at the crack propagation, especially in the second stage here, crack growth, if we look at fracture surface with a scanning electron microscope, it is quite easy, for example, to distinguish these fatigue striations. So each of these striations here is a marker of the crack advance during crack propagation at each cycle of loading. And it can take place at length scales in the order of a few microns in the microstructure, so inside of the grains of the materials. So how does it propagate in the material? So you have the material that is in the presence of a crack. Again, because of the stress concentration ahead of the crack, then you have a local plastic zone. So because of this plastic zone, there is the small tiny surfaces created during the cycling behavior. And when the stress reverses to either to zero to compressive stress, then the crack advances a little bit, and this is what is leading to these fatigue striations. And when you load at a very high stress, such as in the low cycle of fatigue regime, with the stress close to the yield strength, or even higher than the yield strength, then again, the only most let's say difference with the high cycle fatigue will be that you will have a much larger plastic zone ahead of the crack tip, and a much larger fracture process zone in which all of these mechanisms related to ductile initiation, also of coalescence of cavities may occur again. And inside of this plastic zone, again, the crack will start to propagate, and cycle after cycle will go to the point at which the component may be able to break at a critical crack size. So this is, I see I have to stop quickly. So again, even if the material is loaded at constant amplitude of stress, but the fact that the crack is increasing, it means, in fact, that the stress intensity factor, as we discussed it before, it is in fact not constant. So the stress, the remote stress is constant, but since the crack propagates, then the stress intensity factor that depends on the stress, but also on the crack, this stress intensity factor increases. And since the stress intensity factor increases, even at constant stress, then the crack propagation rate increases. And this is usually described with the Paris law. So this fatigue propagation law, Paris law, describes how the celerity of the crack increases in such log scale as a function of the increase of the stress intensity factor, which is again itself increasing because of the increase of the crack size during fatigue propagation. So this propagation Paris law is quite useful for the assessment, let's say, of fatigue propagation in materials exhibiting pre-cracks. So this is, I think, the last slide. Just to tell you that it is very common in fracture investigation, and especially fatigue fracture, to look at fracture surfaces. So we already discussed about fracture surfaces in the case of ductile fracture behavior with the dimples here that we can see using scanning electron microscopes. We can also analyze or retrieve the features of cleavage fracture just looking at the fracture surfaces in a scanning electron microscope. But again, if we do the same in the case of fatigue, then we can, if we look close enough, distinguish these fatigue striations, so how fast the crack was advancing during the loading process. And if we look at the fracture surface globally, then the fracture surfaces offers many details that would allow, for example, the forensic examination of the causes for fracture. It is not unusual to be able to retrieve the initiation site for the fatigue tracks, the one that led to fracture, to distinguish on the fracture surface how fast and how long the crack could propagate during fatigue crack propagation in a stable way, and distinguish in the end the final domain in which fast fracture, so catastrophic fracture, occurred in the material. So again, last message here, a lot can be learned when you look at the fracture surfaces of materials, even here in the case of cyclic loading. So with this, I have to conclude. I tried to show you. I'll try to show you today that all materials, all classes of materials, depending on how they were produced, usually contain defects. Defects may be small, may be large, depending on the way the material was produced. And what makes a difference between materials is the way they behave in the presence of such defects when loaded mechanically in tension or in compression, so when loaded in service conditions. So we had to distinguish between the ductile behavior and the brittle behavior. And we also said that one of the most important properties here for describing fracture properties is this fracture toughness, K1C, or its dual analog, this J1C energy for fracture energy or toughness. Okay, and in the case of fatigue fracture, we just presented that even at low stress levels, the cyclic loading of a material can propagate even very small initial cracks, small initial defects in the material. And these small defects can propagate and can be described in terms of propagation using such propagation law with the Paris law, for example. Okay. Okay, I will stop here. And well, if you have questions, I will be happy to answer.